The morning of November 23rd, 1944, inside a heavily guarded hangar at Tachikawa Airfield, west of Tokyo, a team of Japan's most experienced aviation engineers gathered around wreckage that would shatter every assumption they held about American engineering capability. The aircraft before them, a Boeing B-29 Superfortress that had crash-landed near the coastal town of Suzu after sustaining battle damage, looked massive even in its broken state. But size wasn't what would shake these men to their core. What waited inside that twisted fuselage would force them to confront an uncomfortable truth. Everything Japanese military intelligence had told them about American aviation technology was catastrophically wrong. The team leader, a senior engineer from Mitsubishi Heavy Industries, approached the bomber's midsection, where salvage crews had cut away damaged panels to expose the internal structure. According to technical intelligence reports filed with the Imperial Japanese Army Air Force in the weeks that followed, what he saw in those first moments of examination seemed impossible. 4 gun turrets, each mounting multiple heavy machine guns, positioned along the fuselage, but no gunners sitting in them. Instead, a maze of electrical cables, mechanical linkages, and what appeared to be sophisticated control mechanisms ran throughout the bomber's interior, all connected to remote sighting stations, where crew members could operate the turrets from pressurized compartments hundreds of feet away. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This wasn't supposed to exist. Japanese engineers had heard intelligence rumors about American experiments with remote turret systems, but the prevailing assessment dismissed such technology as impractical for combat conditions. Remote gun control required solving problems in Tizer ice, electromechanical engineering, fire control computation, and systems integration that Japanese technical experts believed exceeded even Germany's capabilities. Yet here it was not on an experimental prototype, but on a production aircraft that bore clear signs of operational service. The wear patterns on components, the standardized manufacturing marks, the robust construction designed for field maintenance, everything indicated this wasn't a one-off experiment. American industry was building these sophisticated systems in quantity. The story of how Japanese engineers came to examine this bomber, and what that examination revealed about the technological gulf between Japan and the United States, begins not in November 1944, but years earlier, when Japanese aviation doctrine was being shaped by a very different understanding of American industrial capability. Throughout the 1930s, Japanese aeronautical engineering earned genuine international recognition. When the Mitsubishi A-6M0 fighter entered service in 1940, it outperformed virtually every Allied aircraft it encountered in the Pacific War's opening campaigns. Japanese pilots flying Zeros achieved kill ratios that seemed to confirm Japan's technological superiority. The Zero could outmaneuver American fighters, had exceptional range exceeding 1,900 miles with drop tanks, and demonstrated engineering elegance that Western observers initially couldn't match. This success reinforced beliefs within Japan's aviation industry about the fundamental differences between Japanese and American design philosophy. Japanese engineers operated under severe resource constraints. Japan's aluminum production in 1941 totaled approximately 100,000 tons annually compared to America's 600,000 tons. Unable to match American material abundance, Japanese designers pursued excellence through minimalism. Every kilogram mattered. Every component was optimized for multiple purposes where possible. Weight reduction wasn't just a design goal, it was an engineering religion. According to technical documents from Mitsubishi and Nakajima, Japan's primary aircraft manufacturers, design teams took pride in achieving superior performance with fewer resources. University programs emphasized theoretical elegance and material efficiency. Engineering students at Tokyo Imperial University studied weight reduction techniques with intensity that bordered on obsession, The goal wasn't just building aircraft, it was demonstrating Japanese engineering superiority through refined, elegant solutions that did more with less. This philosophy produced remarkable results in the war's early years. Japanese torpedo bombers demonstrated precision that devastated the United States Navy at Pearl Harbor. The Nakajima Ki-43 fighter maintained the tradition of extreme maneuverability through lightweight construction. Technical specifications filed with imperial military authorities showed these aircraft meeting or exceeding performance requirements while using substantially less material than American equivalents. Japanese military leadership reinforced this technological confidence through official doctrine. Strategic planning documents from 1941 acknowledged American industrial capacity, but dismissed it as inefficient. Intelligence assessments preserved in Japanese military archives show analysts believed American mass production sacrificed quality for quantity. Japanese pilots received training emphasizing that American aircraft would be numerous but inferior, a quantity versus quality equation that Japan could overcome through superior pilot training and aircraft performance. When intelligence reports describing a new American strategic bomber reached Japanese analysts in 1943, the specifications seemed designed to intimidate rather than describe an actual aircraft. Estimates portrayed the B-29 as impossibly ambitious, a bomber supposedly capable of flying 3,250 miles at altitudes exceeding 30,000 feet while carrying 20,000 pounds of bombs. Japanese engineers calculated such an aircraft would require engines and systems that exceeded known American manufacturing capabilities. Japan's own long-range bomber program provided the reference point for this skepticism. The Nakajima G-8N, planned as Japan's strategic bomber, struggled with development challenges despite far more modest performance targets. Nakajima engineering reports document how building a bomber that could reach 400 miles per hour and operate effectively above 30,000 feet stretched Japanese metallurgy and engine technology to breaking points. If Japan faced such challenges with its refined engineering approach, how could America's supposedly crude mass production methods achieve superior results? The defensive armament rumors seemed particularly implausible. Intelligence reports mentioned remote-controlled gun turrets and centralized fire control systems, allowing a single gunner to operate multiple turret positions. Japanese engineers understood such systems existed. In theory, German designers had experimented with remote turret concepts, but implementing them reliably in combat conditions appeared extraordinarily difficult. Japan's own attempts at advanced fire control systems encountered severe technical obstacles, synchronizing multiple gun positions, creating reliable electromechanical control systems, solving the computational challenges of remote targeting all presented problems Japanese engineers hadn't fully solved even in laboratory conditions. By mid-1944, photographic reconnaissance confirmed the B-29's existence, but Japanese analysts still questioned performance claims. Photographs showed a large bomber, but visual evidence couldn't verify pressurization systems, effective sealing, actual range, or defensive system functionality. Intelligence assessments circulated through Japanese military aviation commands suggested the B-29 represented American propaganda, impressive in appearance, but likely compromised in actual combat capability. This skepticism wasn't entirely irrational. Japanese intelligence had accurately identified real problems in early B-29 development. The Wright R-3350 engines did suffer from overheating issues and in-flight fires during rush deployment. Initial B-29 operations from China in June 1944 encountered significant mechanical problems. Japanese intelligence reports documented these difficulties and interpreted them as confirmation that the B-29's ambitious design exceeded American engineering capacity to implement reliably. Japanese analysts also noted that early B-29 raids caused limited damage relative to resources such aircraft supposedly required. The November 1, 1944 raid on Tokyo, The first B-29 attack on the Japanese capital involved 111 bombers, but achieved minimal destruction due to high-altitude bombing inaccuracy and weather conditions. Damage assessment reports filed by Japanese civil defense authorities show the raid destroyed only a handful of targets in the Nakajima aircraft plant complex. To Japanese analysts, this validated their assessment. The B-29 was an expensive American experiment, failing to justify its resource investment. But then came November 23, 1944, and the crash landing near Suzu. For the first time, Japanese engineers would examine an intact B-29 airframe and systems. What intelligence photographs couldn't show, what skeptical assessments had dismissed, would become undeniable physical reality. The crashed bomber was transported to Tachikawa under extraordinary security. The Imperial Japanese Army Air Force assembled a technical intelligence team, including senior engineers from Mitsubishi, Nakajima, and military research facilities. These weren't junior analysts, they were men who had designed the Zero and other frontline Japanese aircraft. Their expertise made what they discovered all the more devastating to Japanese military confidence. The examination began systematically with external measurements and structural analysis. The B-29 measured 99 feet in length, with a 141-foot wingspan larger than expected but not impossible. The aircraft's weight, however, immediately challenged Japanese assumptions. Even stripped of fuel and ammunition, the airframe weighed substantially more than Japanese bombers of comparable size. The engineers' calculations suggested either inefficient design or the presence of systems and capabilities not visible from external examination. The pressurization system became the first major revelation. Japanese engineers possessed theoretical knowledge of cabin pressurization, but implementing it reliably in combat aircraft remained beyond Japan's industrial capability. The B-29's pressurization system wasn't experimental or fragile. It was a robust, production-engineered solution, maintaining sea-level pressure at 30,000 feet. The examination revealed the system's sophistication: pressure regulators, sealed bulkheads, reinforced fuselage structure, and integration with environmental systems. Technical notes from the examination show engineers calculating that designing and manufacturing such a system required precision machining, quality control, and materials science capabilities Japanese industry couldn't currently match. But the pressurization system merely prepared these engineers for the aircraft's most shocking feature: the remote-controlled gun turrets. The B-29 mounted 4 General Electric remote turret systems, 2 dorsal turrets, 1 ventral turret, and 1 tail turret containing a total of 10 Browning M250 caliber machine guns. What made these turrets revolutionary wasn't the guns themselves, but how they operated. The Japanese engineers' documented examination shows gunners didn't sit in the turrets. Instead, they operated them remotely from pressurized sighting stations, using a centralized fire control system that seemed impossibly sophisticated by Japanese standards. The technical intelligence report described the system's operation. Gunners viewed targets through computing gun sights that calculated lead angles, projectile drop, and range corrections automatically. The gunner tracked the target, while the system computed the firing solution and transmitted electrical signals to remote turrets, which rotated and elevated to calculated firing positions. A single gunner could control multiple turret positions simultaneously, switching between them as tactical situations required. Japanese engineers examined the electromechanical components making this system possible: motors, gearing, sensors, control circuits with what reports describe as profound disbelief, creating reliable electromechanical systems functioning in combat conditions, at altitude, in extreme temperatures, and under combat stress, represented an engineering challenge Japanese technical teams hadn't solved. Germany had experimented with remote turret concepts, but implementing them as standard production features in frontline bombers seemed to require manufacturing precision and reliability engineering exceeding Axis capabilities. The computing gunsight mechanism particularly stunned the examination team. Technical analysis shows the sight incorporated mechanical analog computers calculating complex ballistic solutions in real time. Japanese engineers understood the mathematics involved bullet trajectory, target motion, parallax correction, altitude compensation, but translating those calculations into mechanical devices functioning reliably in combat represented manufacturing and design sophistication they hadn't anticipated from American industry. What made the discovery more psychologically devastating was the realization that these systems weren't experimental. The crashed B-29 showed wear patterns consistent with operational use. Components bore manufacturing marks indicating mass production. The engineer's assessment concluded these remote turret systems weren't rare prototypes installed on special aircraft. They were standard equipment on every B-29, meaning American industry was manufacturing them in quantity. The engineering team calculated implications. Each B-29 required 4 complete remote turret systems, each system containing hundreds of precision components, electric motors, gearboxes, sensors, control circuits, ammunition feed mechanisms. If American intelligence estimates were accurate, and the United States planned to produce thousands of B-29s, then American industry was manufacturing these sophisticated electromechanical systems in quantities Japanese engineers considered impossible. The examination continued for weeks as engineers documented every system and component. The Wright R-3350 engines, despite documented early problems, represented a power-to-weight ratio Japanese engine manufacturers hadn't achieved. Each engine produced 2,200 horsepower from 3,350 cubic inches of displacement using turbochargers, operating reliably at extreme altitudes. Japanese technical assessments indicate the metallurgy and precision machining required for these engines showed American manufacturing capabilities substantially beyond Japanese estimates. The aircraft's long-range fuel systems revealed another technological gap. The B-29 carried 98 gallons of fuel in multiple self-sealing tanks integrated throughout the wing structure. Self-sealing fuel tanks weren't new, both sides used them, but the B-29's tanks demonstrated manufacturing quality and reliability, impressing Japanese engineers. The fuel system incorporated electric transfer pumps, pressure regulation, and management systems reflecting sophisticated systems engineering. Perhaps most significantly, engineers examined the aircraft's maintenance requirements and discovered something challenging fundamental assumptions about Japanese versus American design philosophy. The B-29 wasn't optimized for minimum weight or maximum theoretical performance. It was optimized for reliability, maintainability, and operational effectiveness. Components were modular and accessible. Systems included redundancy. Design prioritized keeping the aircraft operational under field conditions rather than achieving absolute performance through weight reduction. This represented a completely different engineering philosophy than Japanese designers pursued. Where Japanese aircraft squeezed maximum performance from minimum resources, the B-29 achieved superior overall capability by using abundant resources to create robust, reliable systems. The comparison wasn't crude versus refined, it was two fundamentally different approaches to aviation engineering, and the American approach was proving devastatingly effective. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Technical Intelligence Team's reports, Fragments Surviving the War, reveal growing recognition that Japan faced not just a capability gap, but comprehensive industrial and technological disadvantage. The B-29 wasn't just a better bomber, it represented integration of advanced technologies, manufacturing, precision, materials, science, systems, engineering, and quality control at a scale Japanese industry couldn't currently match. Senior engineers from the examination team briefed military leadership on their findings. Post-war interviews with Japanese aviation officials indicate these briefings created profound dismay among commanders who believed Japanese technological excellence could overcome American numerical superiority. The B-29 demonstrated America possessed both numerical superiority and technological sophistication, exceeding Japanese capabilities in critical areas. Some Japanese engineers argued individual systems could be replicated if resources were prioritized, but technical intelligence assessment reached grimmer conclusions. The B-29 wasn't just sophisticated in individual components, its entire design reflected industrial capabilities and systems integration. Japan couldn't duplicate without fundamental changes to manufacturing, base, engineering practices, and resource allocation. Changes that couldn't happen during wartime conditions. Intelligence gathered from the crashed B-29 reached Japanese military leadership and senior government officials through classified technical briefings in December 1944 and January 1945. Post-war testimony from Japanese officials shows these briefings created sharp divisions between military commanders, dismissing findings as defeatist and civilian technical experts, understanding the implications. The remote-controlled turret systems became focal points of internal debates about Japan's strategic position. Military commanders argued Japanese pilots could overcome technological disadvantages through superior training and fighting spirit, the same arguments rationalizing early war successes. But engineers who examined the B-29 understood remote turrets represented more than advanced weaponry. They demonstrated systematic American advantages in electromechanical engineering, precision manufacturing, quality control, and systems integration, affecting every aspect of technological competition. Japanese aviation engineers attempted developing countermeasures based on examination findings. Research reports from Imperial Japanese Army Air Force Technical Division show engineers studied tactics for attacking B-29 formations from angles minimizing exposure to remote turrets' fields of fire. They calculated diving attacks from high altitude might exploit brief gaps in defensive coverage. Fighter pilots received briefings on B-29 defensive capabilities based on intelligence from wreckage examination, but tactical adaptations couldn't overcome fundamental capability gaps. Japanese fighters struggled reaching the B-29's operational altitude of 30,000 feet with sufficient performance to engage effectively. The Nakajima Ki-84 and Kawasaki Ki-61 could reach those altitudes, but their performance degraded significantly in thin air. Combat action reports from Japanese fighter units show pilots who successfully intercepted B-29 formations found themselves attacking bombers that could defend effectively from multiple angles simultaneously while maintaining formation integrity. Japanese bombers couldn't achieve under similar pressure. The crashed B-29 examination also prompted urgent reassessment of Japan's strategic bombing defense requirements. Military planners had designed air defense systems around assumptions that American bombers would operate similarly to Japanese bombers at lower altitudes, in smaller formations, with conventional defensive arrangements. The B-29 invalidated these assumptions. Civil defense planning documents from early 1945 show officials recognized Japan's industrial cities faced a bombing campaign existing air defense infrastructure couldn't effectively counter. Some Japanese engineers proposed attempting to replicate B-29 systems, or at least develop comparable capabilities. Nakajima engineers examined the possibility of creating remote turret systems for Japanese bombers. Technical feasibility studies surviving the war show engineers concluded that while individual components could theoretically be manufactured, Japan lacked integrated manufacturing capability, quality control systems, and materials availability to produce reliable remote turret systems in quantity. The engineering challenge wasn't just designing the system, it was manufacturing it with sufficient precision and reliability to function in combat conditions. The B-29's pressurization system prompted similar conclusions. Japanese engineers understood the principles and had examined functional examples in the crashed aircraft, but implementing pressurization required precision machining of seals and components, specialized materials for pressure vessels, and quality control. Japanese industry struggled to achieve consistently. Mitsubishi engineering reports show attempting to add pressurization to existing aircraft designs would require fundamental redesigns, delaying production for years while American bombers were already operating over Japan. By February 1945, the strategic situation made these technical discussions increasingly irrelevant. General Curtis LeMay's decision to switch to low-altitude nighttime incendiary raids temporarily bypassed the B-29's high-altitude advantages, but also demonstrated the aircraft's operational flexibility. The same bombers operating at 30,000 feet could execute devastating low-altitude missions against Japanese cities. The March 9th through 10th, 1945 firebombing of Tokyo killed an estimated 100,000 people and destroyed 16 square miles of the city. Subsequent raids on Nagoya, Osaka, and Kobe demonstrated American air power could strike Japanese cities at will. Japanese engineers who examined the crashed B-29 understood the technological gap they documented was now manifesting in strategic consequences. The sophisticated bomber they studied in that hangar at Tachikawa wasn't an isolated achievement. It represented systematic American advantages Japan couldn't overcome through willpower or tactical innovation. Some engineers attempted briefing senior military leadership on implications. Post-war interviews indicate these briefings met resistance from commanders considering technical assessments irrelevant to fighting spirit and national determination. The cultural divide between engineering realism and military ideology widened as Japan's strategic position deteriorated. Engineers could document American technological superiority, but military culture struggled, accepting such advantages might be decisive. The technical intelligence gathered from the B-29 examination did influence some Japanese planning. Navy aviation records show engineers used information about B-29 capabilities to design kamikaze tactics, specifically targeting bomber formations. If Japanese aircraft couldn't defeat B-29s through conventional combat, suicide attacks might succeed by overwhelming remote turret defenses through simultaneous approaches from multiple angles. This tactical adaptation acknowledged the B-29's technological superiority while attempting to counter it through desperation measures. Earlier Japanese doctrine would have considered unthinkable. Individual Japanese engineers experienced the B-29 revelation differently. Some post-war memoirs describe feelings of betrayal not by military leadership, but by pre-war intelligence and propaganda, characterizing American engineering as crude and inefficient. Engineers who believed in Japanese technological superiority found themselves confronting physical evidence. Those beliefs were built on incomplete understanding of American industrial capabilities. Other engineers reportedly felt resignation rather than shock. Post-war testimony shows some technical experts had privately questioned the sustainability of Japan's war effort against American industrial capacity, but kept those doubts private in an atmosphere discouraging dissent. For these individuals, the B-29 examination confirmed fears they hadn't openly expressed. The psychological impact extended beyond individual engineers to affect Japanese aviation industry morale. Workers at Mitsubishi and Nakajima facilities were producing fighters and bombers using techniques emphasizing material economy and manufacturing efficiency. Meanwhile, American industry was producing aircraft like the B-29, incorporating sophisticated systems Japanese factories couldn't duplicate. Labor reports from Japanese aviation plants show production workers heard rumors about the captured B-29's advanced features, and those rumors undermined confidence in Japan's ability to achieve technological parity. By summer 1945, Japanese engineers were examining wreckage from other American aircraft, P-51 Mustang fighters, B-24 Liberator bombers, and various other types. Each examination revealed similar patterns. American aircraft weren't crude or inefficient. They reflected sophisticated engineering, prioritizing different design goals than Japanese aviation pursued. The cumulative weight of evidence made it impossible to maintain the fiction that Japanese technological superiority would overcome American numerical advantages. When atomic bombs destroyed Hiroshima and Nagasaki in August 1945, some Japanese engineers reportedly felt those weapons represented the logical conclusion of the technological trajectory they documented, starting with the B-29 examination. America possessed not just superior conventional weapons, but had achieved breakthrough technologies Japan couldn't counter. The engineering gap wasn't closing, it was widening. The Japanese engineers who examined the crashed B-29 in 1944 lived through the war's final months, knowing what their findings meant. Post-war interviews preserved in occupation-era records show several engineers from the technical intelligence team described feeling helpless, watching American bombing campaigns intensify, while military leadership continued, emphasizing willpower over technological reality. After Japan's surrender in August 1945, American occupation forces sought out Japanese aviation engineers for intelligence purposes. The technical assessment reports these engineers filed about the B-29, including detailed documentation of remote turret systems, provided valuable insights into how Japan understood American capabilities. Occupation records show American intelligence officers were initially surprised by Japanese technical analysis sophistication. The engineers hadn't dismissed the B-29 as propaganda or refused acknowledging American advantages. They documented those advantages precisely and reported of them accurately. The failure wasn't in Japanese technical intelligence, it was in military leadership's unwillingness to act on that intelligence. Some Japanese engineers who examined the B-29 participated in the post-war reconstruction of Japan's aviation industry. Memoirs published decades later describe the B-29 examination as a pivotal experience, changing how they understood engineering philosophy. The American approach, using abundant resources to create robust, reliable systems, rather than pursuing maximum performance through minimum materials, became influential in post-war Japanese manufacturing culture. The concept of building quality through systematic processes, rather than achieving it through material scarcity and individual craftsman excellence, became central to Japan's post-war industrial development. Some historians noted connections between engineering lessons Japanese technical experts learned from examining American equipment during the war and quality control methodologies, later characterizing Japanese manufacturing. The B-29 wasn't just a bomber, it was a lesson in systems engineering, influencing how Japanese industry approached design and manufacturing after the war. Individual engineers processed the experience differently. Post-war correspondence and memoirs show some felt betrayed by pre-war education and propaganda, teaching them to dismiss American engineering. One Mitsubishi engineer who participated in the B-29 examination wrote in a private memoir, "The experience taught him to question institutional narratives about technological superiority and to evaluate capabilities based on physical evidence rather than cultural assumptions." Other engineers expressed frustration about military culture, preventing honest technical assessments from influencing strategic planning. Testimony collected by occupation researchers shows several engineers described attempting to brief senior military commanders on implications of the B-29's technology, only to be dismissed as defeatist or accused of being insufficiently committed to national defense. The institutional culture producing early Japanese military successes proved incapable of adapting when those same assumptions encountered contradictory evidence. The remote-controlled turret systems, shocking Japanese engineers in 1944, became standard features on post-war military aircraft worldwide. The engineering principles General Electric developed for the B-29's defensive systems influenced subsequent generations of aircraft weapons and fire control technology. What seemed impossibly sophisticated to Japanese engineers in 1944 became foundational technology for Cold War-era aviation. The B-29 marked a transition point where aircraft ceased being primarily mechanical devices and became integrated electromechanical systems requiring sophisticated controls and automation. Japanese aviation engineers observed this technological trajectory from a uniquely informed perspective. They examined the B-29's systems at a point when such technology seemed almost magical in sophistication, then witnessed how those innovations became commonplace in subsequent decades. Later professional writings by Japanese engineers who participated in wartime technical intelligence programs show the experience reinforced a principle becoming important in post-war Japanese industrial culture. Understand your competitor's capabilities accurately, even when that understanding is psychologically difficult. The story of Japanese engineers examining the crashed B-29 became part of Japan's broader reckoning with wartime strategic failures. Unlike battles attributable to tactical mistakes or individual leadership failures, the B-29 revelation demonstrated systematic miscalculation of American industrial and technological capabilities. Post-war Japanese military histories and academic studies used the B-29 intelligence assessment as an example of how institutional culture and propaganda can create blind spots, preventing realistic evaluation of strategic challenges. Some former Japanese military officers disputed the significance of the B-29 examination in post-war years, arguing technological disadvantages were less important than other factors in Japan's defeat. But engineers who examined the aircraft and documented its systems maintained the B-29 represented something crucial, proof that American industry could achieve both quantity and quality simultaneously. The assumption that Japan could offset American numerical superiority through technological excellence was demonstrably false, and the crashed B-29 provided undeniable physical evidence of that reality. By the 1970s and 80s, as Japan emerged as a global manufacturing power, some former engineers published memoirs and technical histories reflecting on the wartime B-29 examination. These accounts often drew explicit connections between lessons learned from studying American engineering and principles guiding Japan's post-war industrial success. The emphasis on reliability, systems integration, quality control, and manufacturing precision characterizing Japanese automotive and electronics industries echoed engineering principles that shocked Japanese technical experts when they examined the B-29. The irony wasn't lost on these engineers. Japanese industry eventually achieved manufacturing excellence partly by adopting principles demonstrated by the same American aircraft that devastated Japanese cities. The B-29 was both destroyer and teacher, a weapon revealing the consequences of industrial disadvantage, and a model for systematic engineering approaches later characterizing Japanese manufacturing resurgence. In November 1944, inside that guarded hangar at Tachikawa Airfield, Japanese engineers touched the physical embodiment of their nation's strategic miscalculations. Those 4 remote-controlled turrets, operated through computing gun sights and centralized fire control, represented more than American ingenuity. They demonstrated an industrial and engineering capability gap Japanese leadership refused to acknowledge until evidence became impossible to deny. The engineers who examined the crashed B-29 documented the truth with scientific precision, filing technical reports that accurately described what they found. Their analysis was rigorous, their conclusions sound. But in a military culture that valued fighting spirit over material reality, technical truth couldn't compete with ideological certainty. The engineers had touched the future of aviation technology at the moment when Japan's wartime assumptions collided with American industrial reality. What they learned in that hangar wasn't just about one remarkable aircraft. It was about the cost of believing institutional narratives over physical evidence. It was about the price nations pay when propaganda shapes strategic planning more than engineering assessments. It was about the gap between what leaders want to believe and what reality will permit. Those Japanese engineers lived the rest of their professional lives, carrying knowledge that might have changed strategic decisions if military leadership had listened. They documented American technological sophistication that exceeded Japanese capabilities across multiple dimensions, not because American engineers were inherently superior, but because American industry could deploy resources, implement quality control systems, and integrate complex technologies at scales Japan couldn't match during wartime conditions. The B-29 they examined represented more than technological achievement. It embodied an industrial philosophy that Japanese engineers, educated to do more with less, initially couldn't comprehend. American engineers didn't pursue elegant minimalism. They pursued robust effectiveness through systematic engineering and abundant resources. Both approaches reflected genuine engineering skill, but in total war between industrial powers, the approach backed by greater material resources and manufacturing capacity proved decisive. For the Japanese engineers who spent weeks examining that crashed bomber, understanding came too late to matter strategically, but early enough to haunt them. They saw the future in that hangar, a future where American bombers would appear over Japan in formations of hundreds, each aircraft carrying those sophisticated remote turret systems, each mission demonstrating capabilities Japanese engineers had documented, but Japanese military culture refused to accept as decisive. The story of that examination, preserved in fragmentary technical reports and post-war testimonies, stands as a reminder that engineering reality eventually asserts itself regardless of what ideology prefers to believe. The Japanese engineers fulfilled their professional obligation. They examined the evidence, documented their findings, and reported accurate conclusions. That their nation's leadership chose not to act on those conclusions reflected failures of military culture and strategic judgment, not failures of engineering analysis. In the decades after the war, as Japan rebuilt and eventually became a manufacturing powerhouse, some of those engineers found bitter validation. The principles that shocked them in the B-29 robust systems engineering, quality through process control, reliability over theoretical performance limits, became hallmarks of Japanese industrial excellence. The teacher had been a weapon designed to destroy Japanese cities. The lesson, once learned, helped transform Japan into an industrial power. But in November 1944, standing in that hangar at Tachikawa, those engineers understood only that everything that in training had taught them about American engineering was wrong. The bomber before them wasn't crude or inefficient. It was sophisticated beyond anything Japanese industry could produce under wartime conditions. And knowing that truth, documenting it precisely, reporting it accurately, none of it would be enough to change the trajectory of a war already decided by industrial realities that military ideology refused to acknowledge. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.